Hey there, and welcome to this video about time complexity analysis and BigOh. So what is time complexity about? Well, roughly speaking, it's about categorizing algorithms into complexity, and it relates to when you are developing software and you're programming, then you can have different complexity classes in your code. So how does this work here? The notation is that you have a concept called BigOh, and it is defined as a classification of for algorithms into the different time classes. So you have BigOh, f of n, and n usually is the size of the input. So BigOh is actually defining kind of an upper bound for how much an upscaling of the problem size will hurt the performance. So if you increase the amount of elements in your list or something, how much will it actually hurt the performance of this algorithm or this code? So you have different, we have different time classes, time complexity classes, and if we should start from the top here, the best one here usually is called constant time. This is when the execution time is independent of the problem size, so we can actually increase the problem size and we will not have any increase in the time in the performance of the algorithm. We also have a logarithmic, which means that this is also really good, meaning that if we double the problem size, we're only adding a constant to the time, so we're not it is slightly worse than the constant time, but still really good if we are sorting elements or we are searching. So then we have linear time, linear. This means that basically if we have a while loop or a for loop, when we double the problem size, we also double the execution time. So if we go from, let's say, 100 elements in the for loop, we will, if we go from 100 to 200, we will double the problem size and we will also double the execution time. So that is linear. Then we have n log n, meaning that it's gonna double it and put an additional amount extra when we double the input size. Okay, so we have some more time classes when we are increasing the execution time really much. The first one is n raised to the power of 2. That is quadratic time. So if we, let's imagine we have two for loops inside of each other, that will result in, if we double the n, the input size, we will actually increase the execution time by 4. And even worse, if we have 3 loops inside of each other, this is going to increase the execution time by 8. Then we can see it goes up there if we have higher n. If we put more loops inside of each other, it's gonna increase the execution time. And that's just, all these classes are polynomial, meaning that the problem size is also the base number. But we have other time classes where it's gonna be exponential, so that will really hurt the performance. And if we take a look at this graph here, we can see how these different time complexity classes relate to each other. We have the gray one here, which is constant, meaning that no matter how much the input size is, it's going to take the same time to execute it. So that is independent of the problem size. If we take the blue BigOh n, that is the linear, meaning that if we have 100 elements in our for loop or whatever, it's going to take maybe 100 milliseconds to execute. If we double it to 200, it will also double the execution time. So that is linear, and that is okay kind of. But if we go to n raised to the power of 2 or 3 or n, this is really painful for the algorithm, because when we start to increase the input size in our loop, for instance, or in our algorithm, it's really gonna hurt the performance. So this kind of relates to data structures, but also algorithms, and we can see that, if we do the algorithms first, sorting algorithm, for instance, if we do the simple sorting algorithms, bubble sort, insertion sort, and selection sort, if we go to the average or the worst case, you can see they will do n raised to the power of 2. So that means that you have basically 2 loops inside of each other that you need to execute. So the average is actually not that good. If we go for more advanced sorting algorithms like timsort and merge sort and quicksort, we will have more optimistic time complexity classes. So we will have n log n, meaning it is almost linear time. And timsort in best case is also linear time. But also the worst case, you can see average or worst case is n log n, meaning that we have linear time and then we have a constant added to it. So there we can see that if you are doing a lot of sorting, these rather simple sorting algorithms will not be so good anymore. And also when we look at these advanced sorting algorithms, they're using all of them, quicksort and merge sort and timsort, they're using recursion to achieve this this time complexity class. If we go for the data structures quickly, we can see that, yeah, if we take an array, basic array, we have constant time in indexing. If we want to index and access an array, we can input the index number 0 or 2, 1 or 2 or 3 or 4, and then we will get the element in constant time. If we have, let's say we're using a hash table, something like this, this will also enable us to get elements in constant time. If we need to search in an array, in a basic array, then we need worst case to go through all the elements, meaning all the elements in our list here. So that is big O of n. Alright, so there are some calculations that how you should calculate big O rules you should stick to. So if you have, let's say you have a constant in front of the n, 2 times n or 3 times, 4 times, that doesn't really matter because it is still the n that really matters. So you can basically throw away the constants and just leave it like n here. If you have on plus o, another, this is kind of the highest value you go for there. And again, if you have multiplication, so if you have one loop and then you have another loop, then you multiply these two. Okay, so here we have an example of how you could do these this BigOh calculations. We have different time classes. We have BigOh1, that is constant time. Then we have, and this could be one statement kind of assigning a variable or something like that. Then we have BigOh 2 times n. So that could be 2 for loops after each other, not nested. Then we have a multiplication, and then we have something inside of parentheses. So we have BigOh n, and then plus BigOh 3. So that could be 3 independent statements, variables, printouts or something like that. And then we have another for loop. So how do we calculate the time class for this? And the net result is going to be n raised to the power of 2. But let's see how this goes. We have the constant here, 2 times n. So regarding the rules, we should not really worry about the constant here, because we're dealing with a loop here, and that is the most important thing. So we have BigOh of n. And regarding the constant times here, it doesn't really matter if we do 3 or 1 in constant time. It is still really fast here. These guys are the one we need to worry about. Okay, so we have BigOh n times BigOh n plus 1. So if we should summarize this part here, the constant time doesn't mean anything in relation to our loop. There could be 1000 elements in this for loop here maybe. So one independent statement doesn't matter. So that is just BigOh n here. Then we have BigOh n, and we have this constant time. And again, this should also be thrown away because it's only one independent statement. So we end up having actually BigOh n times, or multiplied with BigOh n. So that is n raised to the power of 2, because we have one loop then we have another loop inside of it. So the net result is going to be big O n raised to the power of 2. So how does that look in code? We have a piece of code here, and that should mimic the example before, because we have an independent statement here. We have an array being assigned or being allocated with 100 elements. So that's going to be big O constant time. So that could be anything. It could be 1 maybe. Okay, so that is constant time. Then we have a loop, a for loop, running 100 times. That could be 100. That could be more. So the overall time complexity for this code block here would probably be big O n, because we are kind of independent of this value here. That could be variable 100 or 1000 or whatever. So that is the amount of input we have here. Then we have another for loop, also running 100 times, and we're executing one independent statement here again. So that is also 1n, because we're doing this for the amount of our input size. Okay, so that is linear time. And we're running a method, calling a method here. So we're calling another method with our array with 100 elements. And what are we doing in here? Well, we are also having a for loop in here. So that's the for loop here is basically printing out each number. So that's also dependent of the input size. And we can see right here that we have array n, integer array, and we're running as long as we have input. So that could be 100 here as well. So that is big O n running here. So the overall time complexity is n raised to the power of 2, because we have constant time, we have big O n, we have 2 big O n, and then we have actually a for loop in here, because we could take this code and basically replace this with our method call. And probably it's going to be angry because we have 2 times I here, but you can see that we have one loop and then we have a nested loop inside of it. So that is n raised to the power of 2. Okay, I hope this makes sense. So the net result is this time complexity. So what is the point of all this talking here? Well, basically the point should be that you should look at your code when you are programming, because when you are, a lot of problems require you to have several loops inside of each other. But if you can maybe resolve the same problem using recursion, if you are searching or sorting something, then it could be a better choice. Because if you end up having 3 loops inside of each other, 4 loops, 5 loops, it's really gonna hurt the performance. And also if you look at the code here, we know this is 100. So we kind of have control of how many input we have here. But let's imagine that this should be a database call. So we're actually communicating with the database and we are fetching data from a database. So we don't know the actual length here. We don't know how many rows we're going to get from our database. So that could be tricky, because it could be 100, it could be 1 million. So we are unaware of how much it's going to impact the performance. All right, so that is, I think it concludes basically what I wanted to talk about here about time complexity. So that is important to know a little bit about when you are programming, because you need to kind of foresee and think about how is this code gonna perform when we use this in real production life. Thanks for watching, and take care. Bye bye.